Okay, welcome to another session of the course on Introduction to Machine Learning. And this topic is on a continuing discussion of autoencoders. We have already seen what autoencoders are, where we have a neural network where we have an input and we have a series of layers to produce some kind of representation, and we go through another series of, uh, of layers to produce the output. And the output has to be same as the input. So the purpose of this whole process is to create some kind of a representation in between. And we discussed loss functions and other aspects of creating autoencoders. So today it's a somewhat of a specialized topic, which is the nature of the representations that autoencoders can create, and also a discussion of the kinds of manifolds that are created by autoencoders. So the lecture topic is titled Learning Manifolds with Autoencoders. Okay, so let's begin with the slides. Okay, so the topic is learning manifolds with autoencoders. So this is under the whole topic of autoencoders. It's topic number 6, and we'll also do contractive autoencoders, topic number 7. So that's what we have in today's lecture. So within topics in learning manifolds with autoencoders, what are we going to look at is the manifold hypothesis, which states that the data lie on lower dimensional manifold in higher dimensional spaces. And manifold is a precise concept in mathematics, or in the field of topology in mathematics. And how is a mathematical manifold defined? So we look at that. So there's a bit of math in that discussion, but from the point of view of an appreciation of the terminology. And then what is the nature of the manifold in machine learning? And specifying these manifolds using a sequence of tangent planes. We've already seen the idea of tangents and their importance. And there are some specialized autoencoders. So this slide is just a reminder that we have the design of an autoencoder. We have, in this case, the face of a person, which is encoded, and the encoding is some kind of a compressed representation over here. And the decoder's job is to take the compressed representation to reproduce the input. So we train it with the input and the output being the same, so that we get as faithful an encoding and decoding, and we get a representation that is in between. And we can think of this process as in this diagram, this fanciful diagram here. And we have an input X here, which might be a person here. And then the input is being subjected to some process here. I put this down because when I made this slide up, I was in Bangalore, India, and where one of the principal modes of transportation is this vehicle called an auto rickshaw, and that really shakes you up nicely and flattens you into a pancake, right? So I was thinking of encoder is a flattener of this three-dimensional object into a flat object, which is a manifold, right? Um, Actually, it is wrong to say that it is the entire manifold. It's really a point on a manifold. So this person now has become, through this process of encoding, which is doing some squishing of this object and find a particular point on a manifold, whereas all the other variants of this person, and maybe if the arms up or other people and so on, there'd all be different points on this manifold. So here is a manifold, which is some kind of a flattish looking surface. And there is an embedding or a point in this manifold is being created for this. So this object is this embedding on this manifold, we say. So if it is this person with their arms up and whatever, right? I guess it doesn't have any legs, but in any case, so that would be a nearby point, right? So a different person might be a little further away point and so on. And this embedding can be run through a decoder, and the decoder would be similarly a process like this, not exactly the same, a process similar to the encoder, but it's a decoding process. So takes the flattened individual out into creates a three-dimensional person again. That's the RFX. So X goes to RFX. So this is the terminology of autoencode. As we go from X to an embedding on a manifold, and from an embedding on a manifold to RFX, then what about this embedding itself, or this manifold itself is the subject of interest here. So the manifold hypothesis is that the data concentrates around a low dimensional manifold. So this again shows the manifold hypothesis that this person who's being shown as aging from left to right, all these points are on a manifold, which is in this case a one-dimensional curve on this two-dimensional surface, right? Or this is a surface over here in a three-dimensional world, and so each person is on a different manifold or a curve here. So, what is the purpose of studying the nature of these manifolds? Is that some machine learning algorithms have unusual behavior if given an input that is off of the manifold. So it has learned these things, but if you give something off of this manifold, you're not going to be able to predict the kind of performance it might get. Autoencoders take this idea further and aim to learn the structure of the manifold. So they aim to learn the structure of the manifold. What is the nature of this manifold for this data? So the question we can ask is, why does data lie on a manifold? What is the reason that all of the the doughboy, right? The doughboy is, I think I took the doughboy and put him in an auto rickshaw and converted it into a flat paper cutting. So why does all that lie in a low dimensional space? Okay, suppose we want to classify all black and white images, m by n pixels. Each pixel has a numerical value. An image is a single point of dimension n equal to m by n. So any image you can give me is a point in a space of dimensionality m times n, and the m times n could be, if you have a million pixels, that would be a million dimensional space. Supposing we have some images that are all photos of some related object. Like these are all photos of Einstein, Albert Einstein, the famous physics professor. We are restricted on choice of values for the pixels. If I randomly choose pixels out of in this two-dimensional space, I will not be getting Einstein pictures. And therefore, we expect there to be a less freedom of choice. If they're all photos of Einstein, so we're just not going to be using all the random assignments of pixels at all. Manifold hypothesis states that this subset should actually live in an ambient space, that is the n-dimensional space, ambient space. It should live on a space of lower dimension. So it is like a surface in this higher dimensional space. If you're talking about going from million to maybe 100 dimensional space, so it is some kind of a manifold of 100 dimensions, and all of them live on that, or the points are there. Every one of those Einstein pictures is on that. In fact, a dimension much, much smaller than n. So the points are going to be here. All right, so why does this happen? Reason for low dimensional manifolds. Low dimensional structure arises due to constraints arising from physical laws. So we're saying when you rotate an object, there is a physical law as to how it appears based on the lighting conditions, how much rotation, and so on. So this is why the data lies on a continuous surface rather than fall all over the full dimensionality of that space. Actually, they conducted some empirical studies. They looked at a large number of 3 by 3 images. They said, okay, let's look at 3 by 3. It's a very small picture, right? 3 by 3 represented as points in R9. When you have a 3 by 3, there are 9 pixels. So each pixel can have so many values. Depends on the quantization, how many bits per pixel you're going to be using. If you use 8 bits per pixel, so so there is if it 8 bits, there is about 512 values per pixel, right? And 2 to the power of 8 is what is that, 512? Okay. And we have in R9, and it's a 9-dimensional space. 3 by 3 is 9. We say it's a point in R9. So every point is every image is a point in R9, right? And they kept on rotating those 3 by 3 pixels, a very low dimensional image, and they start transforming it by moving the object represented, or translating it, or rotating it, or making some other transformations, and so on. Well, they observed that they lie in R9 is already a 9-dimensional space. It's not like 2, 3, 4, 9-dimensional space. They lie on a 2D manifold known as a Klein bottle, right? So this is a Klein bottle, which is kind of endless over here. So every configuration of 3 by 3 image is some point on the surface over here, right? So the surface of this object, we say it is 2-dimensional, and it lies on a 2-dimensional manifold in this 9-dimensional space, because they were subjecting it to some physical transformations of the object. They were not randomly picking them apart, moving them along, and so on. So this is the nature of data subjected to transformations. Here is actually some interesting experiments. Low dimensional manifolds embedded in high dimensional spaces. So they look at this photograph, image vectors of 3D objects under illuminations, camera views. These are phase sequences. I suppose this person is looking from left to right as we are increasing the illumination, I think, from left to right. And this is slightly rotated. The face is turned more towards the camera, same kind of lighting conditions, more towards the camera, and frontal towards the camera. And again, the lighting is going from the same way, right? So there is a lighting conditions that are being used. So it's the same person just being moved around with different lighting conditions and different views from the camera. And what they're doing here is they took this high dimensional space. Each of them is maybe many pixels. There's that high dimensional space, and every image here becomes a point in that high dimensional space. And they went and plotted the first principal component, second principal component here. And then they started looking at where these images lie here in this lower dimensional space. And so if you started out somewhere over here, as you make these changes, you start moving along, and moving along like that, right? So it's kind of on a one-dimensional curve here, these points lie, all right? So I don't know how they did, maybe here to here and here to there and so on, some sequence here. Ambient lighting, right lighting, left lighting, lighting, and so on were all being used here. And it sounds like these are 3 different people being rotated along here. So there's curve for 1, curve for 2, curve for 3. So the point here is that these are low dimensional manifolds, and they are showing the values in some other space, and it's an extremely low dimensional manifold that they exist on. Similarly, phonemes in speech signals, you're again using principal components analysis and using what are called as discrete Fourier transform features. And they find that the points for speech signals lie on different manifolds here in a low dimensional space. All right, so there is so much about manifolds. So what do mathematicians say about manifolds? It's kind of interesting to look at the formal definitions. It kind of teaches us something about these topics. If you're this is a research topic on manifolds, but anyway, I'm just throwing it in to wrap up the autoencoder discussion. So definition of a manifold. A manifold is a topological space that locally resembles Euclidean space near each point. So it says this, it's a sphere over here, right? And we say an n-dimensional manifold. I should have said maybe it's a 2D manifold. We're just not talking about the surface here. An n-dimensional manifold is a topological space M for which every point x belonging to M, for every x belonging to the surface here, has a neighborhood homeomorphic to Euclidean space Rn. Euclidean space Rn, we're talking about neighborhood points in three-dimensional Euclidean space can be thought of like this. Points have neighboring points in each of the three directions and so on. And here we have a manifold that we can say every point here has some kind of corresponding point on a corresponding Euclidean space here. So it's an n-dimensional manifold has a corresponding. If you think of it as a three-dimensional manifold, then there's a correspondence in R3, and if it's two-dimensional, then in R2 and so on. If it is just a surface, then it's going to be in R2. What is this homeomorphic? Okay, let's take a look at that. It's a mathematical concept. It's known to the topologists. Homeomorphism in topology is also called a continuous transformation. One-to-one correspondence in two geometric figures or topological spaces that is continuous in both directions, right? What are they talking about here? Well, let's see. Look at this donut shape here. This is kind of a surface here. We're just looking at the surface. So these are interesting here. That let's look at the surface of a cube. They're saying surface of a cube is homeomorphic to a sphere here, and it's homeomorphic to a plane, an oval shape here. That is, every point here can be mapped to a corresponding point, and the nearby points here could be nearby points here. This one is more like this donut with a hole. It is a rectangular object with a hole, and that is equivalent to this, kind of weight they use in weight training, right? There's got a ring over here, and that is homeomorphic to this ring here. It's got one hole in it. Here is an object with two holes, or an object with two rings, or an object with two rings. So they're saying this is the homeomorphism they're talking about. One-to-one correspondence in two geometric figures or topological spaces that is continuous in both directions. That is from this to that or that to this. So homeomorphism is in the sense this cube will not be homeomorphic to this donut here, but among these shapes, they're all homeomorphic. So there is an idea of a homeomorphism. Look at that. These are all little complicated things to try and define. There is also another concept you might have come across, those of you who have been exposed to some group theory in mathematics. They talk about a homomorphism in algebra. So while we are talking about a definition of a manifold and a homeomorphy, we might as well look at what is homomorphy. The most important functions between two groups are those that preserve group operations, and they are called homomorphisms. Right? So a group is a set of objects, like set of integers, and a group has a set of objects and an operation, like addition, right? So we say a group consists of a set and an operator. A function f g to h between two groups is a homomorphism when f of xy is equal to f of x times f of y for all x and y in G. See, a group has some operation defined over here. So if you multiply or add, what have you. So f maps the point x to h and maps y to h. And so f of xy, this operation here, is equivalent to f of x times f of y. Then we say that that the function f between two groups is a homomorphism. So it preserves that operation, right? Anyway, so homomorphism seems to have some relationship, but it's mostly about the kind of operation that you can do on one space and the other space. So this one is more about neighborhoods and so on. That's what homeomorphism is. So anyway, this is a kind of a very elementary type of look at some terminology of manifolds, homomorphism, etc. Those of you who are interested, this idea of groups is very interesting because it relates to things like, the Rubik cube, right? The Rubik cube, right? You can take this cubic object and you can rotate a face of it, the front face or the back face or the top face or the bottom face and so on. And you can define an operation of rotation by 90 degrees, rotation by 180 degrees, things like that. So those are the operations. And there is a group, in the sense any kind of setting of the values is a particular value, or the set, and you perform these operations, and you can actually try and give a solution to the Rubik cube problem. The number of possible settings is extremely large. It is exponential, right? It's a huge number of possible combinations of each of the elements in that 3 by 3 by 3 cube. But the number of operations that are needed to go from any arbitrary setting to a perfect setting where every side has its, I think it's a different color, right? So that is apparently of the order of 20 or 25. So whatever be the, if you're handed a Rubik cube with some arbitrary setting, how many steps do you need to convert it into the right one? Is something of the order of 20 or 25, right? But although the number of possible combinations is extremely huge. All right. Anyway, so that's a side trip on group operations. All right. So that's about homomorphism, not homeomorphism. Anyway, we're back to manifold and a better understanding of what do you mean by a manifold. So I have a little bit more on that examples of manifolds here. We say a manifold has a dimension. So how do we say? So we say a 2D manifold is a surface. So the surface of a sphere is 2D. That's what I was saying in my earlier slide. I said 3D. That should have been 2D. So this is a surface of a sphere. All right, it's a 2D manifold. Here is a sheet of paper slightly bent, and that is also a 2D manifold. And we have the surface of a torus, right, of a donut. That again is a two-dimensional manifold. All right, so it is not a three-dimensional, although it's a three-dimensional object. The surface is a two-dimensional manifold, two-dimensional manifold, two-dimensional manifold. It could also be the union of several surfaces too. So a 2D manifold is a surface or a union of several surfaces. And for the purpose of this discussion, we assume manifolds are connected. They're not disconnected. So a 2D manifold is a sheet of paper. something that you put on a surface, or something that you put on a even a donut. And a 1D manifold is a curve. So this is a one-dimensional manifold, a curve like this, or I draw a circle, or we draw a what do you call this? A spiral, right? A spiral, yeah. And we have we saw this example before. So we have the handwritten digit 9 moved vertically around, and it's being represented in a two-dimensional space. We say it is a lower dimensional, one-dimensional object in this two-dimensional space is all these 9. So the manifold is this. So a 2D manifold is a surface, a 1D manifold is a curve, a zero-dimensional manifold is a point. All right. So all of 3 space, R3 is a 3D manifold, right? We said that all of that space is itself a manifold, all right? So R3 itself is a 3D manifold. So these are two-dimensional manifolds. So this is a manifold has a dimension, we say. So the dimensionality for the manifold. Here is an interesting one. 2D manifold in R3 is homeomorphic to R2. So look at this. We have a three-dimensional globe here, and let's say we started at the North Pole, and we drew 2 lines, which were 50 degrees apart, right, at the North Pole. So that traces here this triangular region on the surface of the Earth, and this triangular region we say is homeomorphic to a two-dimensional object here. We're drawing this triangle here and say that corresponds. So this is homeomorphic here for this triangle and this triangle. You can map the corresponding points, and there are neighboring points which should be mapped here and so on. Okay, anyway, so that's an interesting one about normally when we measure distances and all that, we in small areas we look at the straight line distance, and here we have to look at the spherical distances here, right? We know that from planes that are flying. We when we look at the distance between two far-flung cities, we are looking at the what do they call it? The arc distance here, right? Some of the term that they use. Maybe nautical distance, no, not quite that. So there is a polar distance. Anyways, so in mathematics, a manifold is a topological space that locally resembles Euclidean space near each point. Right, so there is Euclidean properties. Topological space may be defined as a set of points along with a set of neighborhoods for each point, satisfying a set of axioms relating points and neighborhoods. So for every point, there's a set of points, the neighborhood points, and some set of axioms relating points and neighborhoods. And this is being mapped from one to the other. So we say these are homeomorphic. This triangular surface here and this triangular surface in 2 dimensions are homeomorphic. Okay, so anyway, we have a rough idea of what is meant by a manifold and what is the mathematical definition of a manifold, which gets pretty complicated in terms of definition of homeomorphism. But let's relate that to machine learning. How does that relate? So manifolds in machine learning. In the observed m-dimensional input space, so we're observing something, the data is distributed on an mh dimensional manifold. So we say that the photographs of Einstein are not really in the full m-dimensional space. They are occupying some much, much lower dimensional space. And let's call that as mh. H is some lower dimensionality. So it's, need not be 2 or 3, it could be larger than that, but it's some MH dimensional manifold. We say that X belongs to Rm, in the sense it belongs to the set of real values in this M dimensional space. X is an input. H belongs to RMH. MH is much smaller than MM, and H is a point in this such that X can be generated by some generative model here, that is the decoder, applied to H gives you back X, right? So this is the nature of the encoding. And we also say G-gen is smooth, okay? So it's a mathematical condition here. Now let's look at this very, very simple case to get a feel for what's going on. We have, let's say, just two variables, x1 and x2. So the dimensionality of the original ambient space is only two. There are only two variables. So m equal to 2, we're saying. And then let's say we go into a one-dimensional space, one-dimensional variable, h, right? H is h nat, it's said here, but let's say it's h. So we're saying this mh, this lower dimensional space, equal to 1. We are going from m equal to 2 to mh equal to 1. And this is a design for an autoencoder. So we should be able to go from here and to reconstruct it back, x1 and x2. So we are finding a representation here that captures x1 and x2, and from which we can go back to x1 and x2. Now this shows a very interesting depiction of what this x1 and x2 could be, some example. And let us say we have along the x-axis a one-dimensional representation, right? This really corresponds to this h nat here. And this shows how the x1 is varying and how x2 is varying. They look like Gaussian normal distributions, but forget about probability distributions for now. This is not probability distributions. Supposing we have an underlying representation, and as this underlying representation changes, the value of x1 goes up and goes down like that. So it is similar to the idea of the illumination and the pose and so on. We saw photographs. So we have, as we move this object, according to, maybe this is the transformation, this object is going up and going down. And the second one is corresponds to x2, it's a feature map. This one starts a little bit later, that also goes up and that also comes down. So we have this relationship between x1, x2, and h as to how they behave. As h increases from a low value from 0, x1 first increases quickly and then starts going down. And then x2 then starts going up and x2 starts coming down. So that's the relationship between h and x1 and x2. If that is the nature of things, then let's say we plot. So here is a x1 and x2 dimensional, two-dimensional representation. And we say, well, let us move this value of h from 0 like that. And how do they look in this x1, x2 dimensional space? So we are doing that plotting here, and this low point here, where x in this point here, x1 is pretty high, but x2 is extremely low, and that point corresponds to something here. x1 is pretty high, but x2 is pretty low. There is this point over here. And similarly, as we go along, we have here x1 and x2 are roughly equal at this point, right? x1 equal to x2. And that at that point maps over here. Now what has happened is x1 has come over to this value, which is about 0.7 or something, and that's also 0.7 for x2. So they're both equal here. And as we come to a point over here, we are here. So you see so in this x1, x2 dimensional space, so what we're saying is x1 may have a range of values, x2 may have a range of values, in which case we have a two-dimensional space of all kinds of values that they can take. But if we are saying x1 is constrained to behave like this and x2 is constrained to behave like that, then the points in this x1, x2 dimensional space, instead of lying, so there could be points anywhere in this x1, x2 dimensional space. For any setting of x1 and x2, you could get points all over here. But because of this constraint we have put, the points just move along a curve like this. As it changes from 0 to, let's say, 100 here, it's going like this and like that and like that and like this. So that's interesting that the whole set of points are now constrained to lie on a one-dimensional manifold and not at an arbitrary points here. So this is the essence of the nature of a manifold, and we are showing it exactly by means of what an autoencoder is doing. It is converting it into a one-dimensional representation, going from two-dimensional space to a one-dimensional representation. Basically, we're saying instead of dealing with x1 and x2, we have got an h nat. This is a one-dimensional variable. There's a certain value here, and each value corresponds to some set of values of x1 and x2. And those values of x1 and x2, as you change h, are going just along this curve here. So we are producing, we can reproduce from the autoencoder x1 and x2, but we've also along the way discovered that the data lies on this low dimensional representation. So this is the crux of the matter. And why is this important is that we can now work with a low dimensional representation rather than a very, very high dimensional space that we originally started out with. Of course, in this case, there was only two here, but that is to illustrate the point. We looked at two-dimensional input data with a one-dimensional manifold. So now the manifolds themselves are specified by tangent planes. So tangents specify how x can change while staying on the manifold. And in a one-dimensional manifold, y equal to f of x at point x equal to x naught is given by y is equal to f of x naught plus f prime of x naught times x minus x naught. That's right. This is the Taylor series expansion. We put in approximately because we are abandoning the higher order derivatives here. Similarly, if you have a two-dimensional z equal to f of xy, so two inputs x and y at point x naught y naught is given by z equal to. So this is how we can represent any point z equal to f of I at the point x naught y naught can be written as in terms of here we have first derivative with respect to x and we have first derivative with respect to y. So at a point x on a d-dimensional manifold, the tangent plane is given by d basis vectors that span the local directions of variations allowed on the manifold. So we are now saying, okay, as long as your data is going to lie on a manifold, let's look at the tangent specify. So how is this manifold changing? So we know something about the points on the manifold and how the manifold is changing locally. So at this point, we are doing a tangent line approximation, one-dimensional manifold here, and there's the tangent line approximation. And then here we have a two-dimensional manifold, which is a surface in a three-dimensional space. And we are again at a point x naught, y naught, we are actually drawing a tangent plane. And we say that the linear approximation Lxy to f of x. So we call that as a linear approximation at that point at point x equal to x naught is given by this in terms of the first derivative. So the y is written in terms of at an x naught. right? So at a point, x naught can be written as f of x naught plus this. So for any arbitrary x naught, I think that's how we can say it. All right, so continuing on this idea, tangents of one and two dimensional manifolds, a one-dimensional manifold in 784 dimensional space. If you have MNest, handwritten digits, with I think something like 28 by 28, that is 784 pixels. And let's say we had an image that is translated vertically. Figure below is a projection into 2D space using principal components analysis. And n-dimensional manifold as a n-dimensional plane. And the tangent is oriented parallel to the surface at that point. And so what we're showing here, first of all, is these are all the images and these are all the manifolds that are the surfaces corresponding to each of the handwritten digits. And then they're looking at a two-dimensional situation for one of the handwritten digits that happens to lie on a line like this. And image shows how this tangent direction appears. So they're drawing tangents at every point to specify the manifold. So, they're showing here MNIST with 3D PCA. Here is the tangent plane. So the tangents at every point, you can calculate the tangent at every point, then that is a specification of the manifold. So an autoencoder performs trade-off between two forces. So learns representation H of training example X such that X can be recovered through a decoder. Well, primarily we're saying we would like to recover this. And that X is drawn from the training data set is crucial. It means that autoencoder need not reconstruct improbable inputs. So we are drawing samples and learns a representation such that we can recover it through a decoder. And it satisfies the regularization penalty in that limits the capacity of the autoencoder. We don't want an exact representation. It's a lossy representation. Either they limit the capacity or it can have a regularization term added to the reconstruction cost, just like we saw in standard neural networks, standard linear regression, standard linear classification. We have a regularization term, omega of h, and so that is added to the loss function. What is the loss function? It is comparing x to g of f of x. F of x is the encoding, g of f of x is the decoding. And so the decoded x should be as similar to x as possible according to the loss function. But this one is a regularizer that says, oh, wait a minute, the representation you use cannot be arbitrary. These techniques prefer solutions less sensitive to the input. Together, they force the hidden representation to capture information about the data generating distribution. So we are trying to learn what is the nature of this data, what is the surface they're going to be on, and by imposing a loss function. And what does the encoder represent? The encoder captures only variations needed to reconstructed training examples. And if data generating distribution concentrates near a low dimensional manifold, this yields representations that implicitly capture a local coordinate system for this manifold. Only variations tangential to this manifold or on X need to correspond to changes in H equal to f of X. Hence, encoder learns a mapping from input X to a representation space, a mapping that is only sensitive to changes along manifold directions, but that is insensitive to changes orthogonal to the manifold. Okay, so let's get a little bit more of a sense here. This one is an interesting example of capturing manifold structure by invariance. So this says when reconstruction is insensitive to perturbations around the data points, encoder recovers manifold structure. Right. So they're showing here a one-dimensional case. Manifold is a collection of zero-dimensional manifold. We earlier on said a zero-dimensional manifold is a point. So this shows here is an x and here is an r of x. So here are values of x, here are values of r of x. And we're saying it's a collection of manifolds. It's saying that there is a point here and a point here and a point here. And we have some, so this, the point defined by this dotted line over here. So, and this blue dotted line is what's called as the identity line. It's roughly the 45-degree line, which produces r of x exactly equal to x. So when we say we are on this point, the reconstruction has to be exactly equal to the input, right? So it's on the 45-degree line. So when you draw a 45-degree line between x and y, it means x equal to y. So that's what's going on here. And so we have, at these points, we have exact reconstruction for these points. And we say that the manifold consists of these 3 points. Data lie on these 3 points, these 3 points. And the optimal reconstruction is anything that's going through those exact points here like that, right? So, so this is an exact reconstruction, and it is invariant to any disturbances, we say. It is insensitive to perturbations around the data points. Autoencoder recovers the manifold structure. So this autoencoder is encoding them, just representing these points using this particular, this is the autoencoder saying that is the manifold. So then why are autoencoders useful to learn a manifold? Okay, autoencoder characterizes a manifold. It represents data on or near the manifold, right? So we want data to be on or near the manifold. If you have a data away from it, then it is not belonging to that particular set we were training on. Representation for a particular example is an embedding. So this question came up in the last class too. What's the difference between encoding, decoding? You can see there are similar terms, and embedding is a particular representation. So embedding means a representation, a nonlinear type of representation, lossy representation, but it's finding a point on a particular manifold is an embedding. It's embedded on that particular manifold. An embedding has a fewer dimensions in the ambient space of which the manifold is a low dimensional subset. And there are other algorithms, non-parametric manifold algorithm discussed in next slide, which directly learn an embedding for each training example. And or we can learn a more general mapping, a function to map points in ambient space to an embedding. So let's look at non-parametric manifold algorithms. This is a fairly simple idea. Non-parametric manifold learning. I'm kind of exposing you all to some research topics in deep learning now. But anyway, why not? We're not doing a lot of that in this course, but here is one area about learning representations. And that's what all of deep learning is about today. What are the appropriate representations for the data? So we can build a nearest neighbor graph where nodes represent training examples, one node per sample, and directed edges indicate nearest neighbor relationships. So let's say there is one of the famous data sets. It's called the Queen Mary University of London multi-view face data set. This face is going from looking left all the way to the front and looking right, and looking up to looking all the way, looking down, and again looking down to the left to looking down to the right. So this is a data set of a person's face. Same person, right? Can you imagine training on one person with this many images and then you're doing it all over for every other person? That's going to be an impossible task. So we are talking about what can we, how can we do this more efficiently, not working with a very high dimensional image space that they're all in. And it says, well, we can think of every one of these faces as a node in a graph, and they are connected by this. So this slight tilt in one direction or something, right? So all these things. So I guess every picture seems to be connected to 6 other pictures here. I suppose if you're in the middle somewhere here, you can go. There are going to be all these neighbors. 1, 2, 3. There's actually 3 plus 3. There's 8 here. Okay, so they have, it could be even more than that, right? I guess there's even more here also, right? It's not just 6. 1, 2, 3, 4, 5, 6. Okay, they've got only 6 of these here. Anyway, so one can decide what is the what is the homeomorphy here, what is the kind of mapping of nearest neighbors and so on. So it says build a nearest neighbor graph where nodes represent training examples, 1 node per sample. Directed edges indicate nearest neighbor relationships. Procedures to obtain tangent plane associated with the neighborhood of the graph, and associate each training example with an embedding vector. So every training sample becomes an embedding vector. And now we are talking about they're all embedded on a particular surface. So the vector changes from here to here, and that those are nearest neighbors. Works when number of examples is large to cover manifold twists. So we have lots of examples. The manifold may be twisting around. We talked about things like Klein bottle and so on, which goes around and comes back again. And so we have a method associates each node with a tangent plane, one that spans the directions of variations associated with the difference vectors between the example and its neighbors. So this non-parametric manifold learning associates planes with the manifold here. And this idea is also extended here, tiling a manifold. A global coordinate system can then be obtained through optimization or by solving a linear system. And a manifold can be tiled by a large number of locally linear Gaussian-like patches or pancakes, because the Gaussians are flat in the tangent directions. So this is being characterized by a discrete number. So the manifold is now represented by a discrete number of Gaussian distributions, and each of them is has a low dimension. And of course, they in a higher dimensional ambient space would be specifying where they are located. So that will become a 2-dimensional plane here. These methods can only generalize the shape of the manifold by interpolating between neighboring examples. Unfortunately, manifolds in AI problems are very complicated, that can be difficult to capture from only local interpolation. So this is one of the early methods to say, well, we've got a representation that all these variations are captured by this manifold. So we can expect all the other objects to behave in a similar way by these kinds of shapes. And how do you represent them? By a set of discrete points and by a set of tangents at these discrete points. That is how it specifies how the shape is changing in this on this manifold. Here is a more concrete example, a medical example, manifold learning in medical imaging. This is an example I came across. I was just looking to see, where can we find some uses for this type of stuff? They're doing, this is the spinal cord. A spinal cord consists of these little segments. I don't know what they call them. There must be a medical term. S1, S through SL, right? So there are a certain finite number of these, right? Spinal cord. And each of these is a bony structure like this. And these bony structures are all represented over here. This is object Sj minus 1, object Sj, object Sj plus 1. And there is a certain angular connections for these. And they were saying manifold induced by articulated based metric. So they're saying these seem to lie along a particular manifold, learned data manifold. And they're saying linear techniques unsuitable for capturing variations in anatomical structure. So if you want to talk about how the spinal cord is twisted or changed and that kind of a thing, the location, and the medical folks, they found that this manifold way of representing it makes sense, that how the spinal cord can vary. So we are going from this object in three-dimensional space to a two-dimensional space, and actually a curve which is a one-dimensional manifold, saying there is the curve and those are the nearby points to that curve that corresponds to any movement of this. So what might be happening if you do some surgery, I don't know what they use it for. Structure in the data in computer tomography or magnetic resonance imaging or ultrasound allows a lower dimensional object to describe the degrees of freedom, such as a manifold structure. So we are able to observe the behavior in a lower dimensional manifold. This is just directly using the manifold as opposed to using the manifold in some kind of a machine learning type of scenario. It's just there can be some use for manifold learning in medical imaging. Okay, this is the very last part is about some variants, which is over complete contractive autoencoder and so on. I think I'm going to, sounds like Mihir and Sugata have planned a very nice session for you guys. So rather than teach you one more contractive autoencoder and its loss function and all that kind of thing, I'm going to yield to them to take up this topic. Okay. All right then. Are there any questions here which I missed along the way? Okay. So
Professor, can you make me the host for this?
okay, hold on. All right, I will Mihir make host. Change host. Okay, you're the host. All right, you guys. What's the topic again, Mihir, today?
The topic is k-means, and that's made by Saugata. So they're
Okay.
building k-means from scratch.
All right. That's it.
Yep, that's it.
You're not going to do anything on autoencoders, huh? Okay.
Autoencoders we did in the last
Oh,
session.
you did it last time. Okay, you're going to do K. Okay, K means is the easy topic, but anyway, looking at the code is always fun. And I'm going to be starting reinforcement learning as next week's topic, okay?